Hi, you're listening to Avril Sauter talking about CCNA Wireless. In this lesson, we're going to talk about propagation basics. So what does propagation mean? It's literally what happens to your signal when it goes from the transmitting antenna to the receiving antenna. So we're going to talk about what's happening to your signal as it goes over the air. So in this picture you can see I've got a source transceiver which is transmitting, and I have a destination transceiver which is receiving the signal. And so when that signal is propagated from the antenna, all sorts of things can happen to it. Now I could have line of sight between the two antennas like I have in this illustration, or there could be some obstacles in between, in which case my signal would need to penetrate through those obstacles. My signal could be bouncing off the ceiling, the floor, the desk, people's bodies, and that is constantly changing. So as people are moving around and my RF environment's changing, so the path of my signal is going to change. And so that what that means is that my received signal is constantly going to be changing. And you can see here that I've got signals coming in at different times, because depending on what path they took, they're going to arrive at different times. Now clearly if I have line of sight, then that signal is going to arrive first, and then all my reflected signals are going to arrive a little bit later. So this is a very challenging RF environment. And so when we talk about what happens to my signal over the air, these are the factors we generally talk about. We talk about absorption, and this is the ability for substances to absorb the energy of my signal. And so if my signal is going between my source transceiver and my destination transceiver, and it is going through maybe a plasterboard wall, it's not going to attenuate very much. But if it's going through reinforced concrete, then my signal is going to attenuate quite a lot. In fact, that wall is going to absorb a lot of the energy, and my signal that comes out of the other side of the wall is going to be significantly weaker than if I was just going through a plasterboard wall. So absorption is the ability for matter to absorb energy, and that includes walls, doors, water, your human body. Everything will absorb energy when it's hit by these signals coming from my antennas. Then we have reflection. Reflection is the ability for a signal to bounce off a surface. If it wasn't for reflection, we wouldn't have wireless LANs today, because very seldom do I actually have line of sight between my transmitter and my receiver. And different surfaces reflect differently. So if I have mirrors which have a silver metallic backing, or if I have metal filing cabinets, then those signals are going to reflect really well off those surfaces, and I'm going to get more of a reflected signal than those surfaces are going to absorb my energy. Then I have refraction, and you've all experienced refraction. I remember playing with this when I was back at high school. And when you put a finger in a bath, if you take a bath and put your finger in and you tilt your finger so it's not going directly into the water and going in at an angle, your finger will look like it's bent. And that is because the light that you're looking at has suffered refraction. But all electromagnetic signals will suffer refraction, and so this is the ability for the signal to actually appear like it's bent after it's come into contact with an object. You can also have scattering. Now down at the lower frequencies below 6 gigahertz, you tend to have more of a reflected signal, and then up at the very high frequencies, when you're up above 10 gigahertz, then you tend to have more of a scattering. And what it is that when the signal hits a building, it literally, rather than reflecting, it scatters. And the reason it happens at the higher frequencies is, remember, at the higher frequencies you have the lower wavelengths, and so when it hits the building or a surface, the wavelength, if it's very small, starts to become equivalent to the roughness of the surface, and so it tends to scatter into multiple directions as opposed to having a very strong single reflected signal. So again, lower frequencies we tend to have more reflection, which is why we don't need line of sight. Up at the higher frequencies, signals tend to scatter, and typically at the higher frequencies you need to have line of sight between the transmitter and the receiver. Multipath we've talked about, that was on the previous slide. You saw that different reflected signals are coming in at different times because they're traveling different paths, and if a path is longer, then it's going to take longer for the signal to travel that path. Attenuation, my favorite. So when a signal goes through free space, it'll attenuate. This is no different than your voice. When you talk, your signal attenuates. So the further away you are from someone that's talking, the weaker the signal is, the harder it is to hear them, and eventually you'll be so far away you won't hear them at all. And so signals attenuate. The higher the frequency, the greater the attenuation. And so remember, we talked about if you're deploying in the 5 gigahertz band, your signal won't go as far for the same transmitted power than if you're at the 2.4 gigahertz band, because higher frequencies attenuate more than lower frequencies. And so attenuation, and all signals attenuate. Wireless LANs, Bluetooth, your voice, cellular phones, everything will attenuate. How much it attenuates and how well you can hear it is a factor of what power level I transmitted at, your antenna gain, and what frequency you're operating in, and the distance you are away from the transmitter. So to continue our conversation about attenuation, and here I'm assuming free space, i.e. you're just line of sight and you're propagating just to illustrate attenuation. The signal gets weaker as you move away, so it starts to deteriorate. And so what I need to do is I need to make sure that I have enough received signal strength to successfully demodulate and decode your signal. And you remember we talked about if I'm close to the transmitter, then I can use higher levels of modulation, maybe all the way up to 64 QAM and get to higher data rates. And as I move away, I have to reduce my modulation encoding because I'm dealing in a more difficult RF environment. My received signal is weaker, and therefore I have to drop my modulation encoding, and therefore my data rate will drop. So I need to make sure that I receive enough signal strength to recover the signal. Now, one of the things to look for when you're looking at specifications of client devices and access points in eRadio is to look at the receiver sensitivity. And the receiver sensitivity is going to tell you, I need to receive this much signal energy in order to be able to demodulate the signal. And the receiver sensitivity will be different for different levels of modulation encoding. So a good specification for a wireless product will say, I need to receive this much signal strength to decode at 64 QAM, this much signal strength to decode at 16 QAM, this much to decode at QPSK, and this much to decode at BPSK. So again, lots of terms here. Received signal strength is what is arriving at the antenna, and what you need to do is you need to make sure that you have achieved the receiver sensitivity that's specific for your device. And different devices have different receiver sensitivities. And when you're planning out your network, you need to accommodate your weakest device. So whatever device has the weakest receiver sensitivity is what you should be using for planning your network, because when they can't recover the signal, then that defines the edge of your cell. So what happens here is if I start to transmit my data, and here in the top diagram I'm sending my data frames, and everything's going really good, and all of a sudden something transmits in my frequency band and causes interference. What happens is that I can't recover those bits. If that interference is stronger than my transmitted signal, then I'm going to lose bits. And in which case I might have to retransmit that frame again. So what I'm looking at here is I'm going to transmit at a certain power level, and when interference occurs, if interference is significantly above the power level that I'm transmitting at, then I'm going to suffer a potential loss of data. What this means is that it's really important for your signal to be significantly above your noise and interference level. And so one of the critical factors that we measure when we're operating our wireless LAN is the signal to noise plus interference ratio, sometimes just referred to the signal as noise ratio. And it really is that threshold value above the interference that allows me to recover my signal and successfully demodulate it and decode it. Now, one of the challenging things, of course, is that interference comes from a lot of different sources, and so, when I put on my microwave oven, I could get some interference. When people start using the cordless phone, it could create some interference. When they're using their Bluetooth device with their cell phone, it could create some interference. Or if my neighbor transmits on the wireless LAN, it could cause interference. And it's really a matter of the interference where you are, where you're trying to receive the signal. That is the signal to interference ratio that you care about. Is at that moment in time, do I have enough signal strength to recover your signal? So very important for you to understand what the signal to noise plus interference ratio is. Typically people just call it the signal to noise ratio, the SNR. So one of the important concepts that you often hear about is a link budget, and it's relatively straightforward. It's a bit like doing a financial plan. When you earn so much money and then you need to buy some things, and then you want to make sure you have some money left over, or at least you don't go into a negative situation. And so doing a link budget is just like that. You want to make sure that you have enough dBs to be able to get to the receiver and to be able to demodulate your signal. And so it basically adds up all the losses and gains and then tells you, yes, whether or not you can actually receive the signal. So in this example down here, I've got an access point that's got a 3 dBi gain. And so you would take the transmit power, you would add 3 dB to it as the antenna gain. In this illustration over the air, I'm saying, hey, I lost 70 dB. So you take 70 dB away. On the receiving side, in this illustration, I have a 2 dB antenna gain, and so I add 2 dB back in, and so the loss and gain relative from the antennas and over the air is 65 dB. So I take my input power, I take away 65 dB, and I want to make sure that I've got more than my receiver sensitivity in order to be able to recover and decode and demodulate my signal. So a link budget is simply adding up the gains and losses to make sure at this transmit power you have exceeded your receiver sensitivity so you can decode and demodulate the signal. And again, the further away you go, the greater your attenuation, and eventually I won't be able to recover the signal with sufficient strength to be able to demodulate it and decode it, and at that point in time you're out of coverage. Well, we've talked about dBs, and so it's time really to talk about what is a dB. And a dB is a ratio between two things, and in this case the ratio between two power levels. You can use dBs to measure all sorts of things, but when we talk about the radio, we're talking about the relative ratio between two powers. And you say, well, why do I need a ratio? Well, the reason why you need to look at it this way is that, let's say you've got an access point that's transmitting at 200 milliwatts. the time it gets to the client that's going to receive that signal and recover it, it arrives about 10 to the minus 10 milliwatts. And so the difference between 100 milliwatts and 10 to the minus 10 milliwatts is a lot of zeros. And it's very difficult to conceptualize what that is. And so by looking at the ratio between those two powers and then taking the log of it, it makes it a number that's more reasonable to be able to quote and to understand. And so when you look at dBs and you look at this chart, if I lose half the power when I transmit over the air, I would say that's a 3 dB loss. If I was to lose 1/10 of the power, then that would be a 10 dB loss. And so it keeps going. And so all a dB is looking at the ratio between two powers and taking the log of it, so the numbers are easier for us to deal with. Now I just want to remind you about a couple of key terms that we talked about in this lesson. The first is the signal to noise and interference ratio. Sometimes people just abbreviate that to the signal to noise ratio. And as it says, it's a ratio and is comparing the signal that you received over the background noise and interference level. The other term is the decibel, which is also a ratio, and a decibel is simply a logarithmic value and looking at the ratio of two values. And here we've been using it to look at the power difference of when I'm transmitting a signal to when I'm receiving a signal, and the log of the ratio of that difference is what we then quote in decibels. Very important to be familiar with both of these two things, and of course they're ratios, and so of course they actually have no value, like you can't say meters or inches. They are ratios of two values. Thank you for listening.